Okay, so here. The simplest case for making something move. Object being dragged with a rope, right? Now, the hardest part about this is I want the object to actually accelerate. So imagine a rope and like a person pulling on the rope at moment in time 0, at your first moment in time, not moving, right? So there's no EK. If our system is this mass, this block, is it an elastic block? No. Is it a rubber band? No. So any elastic to worry about. Any change in height, you think? So just to keep things simple, there's no energy stored in our system in the beginning, right? I'll just call it a block. And EG, EK, E elastic, they all 0. Everybody good? The energy stored in this system, in the end, at moment in time 2, whenever that is, after some period of time has gone by, make sense? So the energy in this same bank later, we're going to have the object moving. Are you guys with me? Everything's good? Now I'll try to draw someone running. Let's see if I can do that. Oh, I'm not very good at this. He's running. Now, keep in mind, what we're really talking about here, between these moments in time, in order for this object to speed up, you have to imagine like an icy, frictionless surface. So imagine that, icy, frictionless surface. How's the guy going to run? It sort of doesn't make sense, okay? The guy has special shoes for running on ice, okay? And he speeds up. And this whole system, block system being pulled, speeds up gradually. Acceleration is to your right. Everybody good? And we're gonna say it's an icy, frictionless surface. And we're gonna say we're gonna ignore dissipated energy. So ignore. So between these moments in time, we don't have any dissipated energy. We don't have any friction. We don't have any air resistance. Are you guys good? And the other assumption I want you to make is that during the period of time, during the time interval, between that moment and that moment, please don't get lost here, between these moments in time, the object is undergoing constant acceleration, and everything you learned last semester related to constant acceleration will apply between these moments in time. You guys good? It's a lot you learned. So really, in 5 minutes, we're just going to summarize everything you've learned. Kind of amazing. Cool? So, all right, constant acceleration in this time interval. That's from that moment to that moment. Is everybody good? There's a lot of assumptions here. But I think this makes the problem simple. Because we don't have any change in height. EG is done for. We don't have any kinetic energy stored in our system in the beginning. It's not moving. I should make a note here that this object is moving with velocity v at that moment in time. So we will have kinetic energy stored in our block in the end. Okay? Is there any elastic? Okay? So our system doesn't have elastic properties that we're going to worry about. Everybody good? So you got money in the bank in the end. Where did this money come from? It wasn't in your bank in the beginning. Good. So you say it came from work. Is there a force on our system responsible? Yeah. The person is not touching the block, but the rope is. So we got work. So essentially the rope is doing work on the block. That's how we would say it. You guys good? Essentially the rope is putting energy into the block because there's a force on our system. So there's energy going across our system boundary through the rope. Everybody good? Now, so the rest of the equation is going to be plus work, right? This doesn't stand for weight. In the context of energy, W is work, right? Yeah. And then this is minus E dis, but we're ignoring E dis, so E dis is 0. And then this gets you your full equation. Is everybody good so far? Again, please stop me if anything doesn't make sense. Let me erase a little bit here. Okay? So essentially work is energy transferred into the system that becomes kinetic energy stored in the motion of the object. Are you guys cool?
Weight or work.
Not weight.
I said work.
Okay. So you have an equation for work based on a F delta X graph, right? F versus delta X. What's it look like in this case? Okay, let me go back for a sec. Keep something in mind here. Please keep something in mind. In order to do this, use your imagination. You drag a block over ice. You have special shoes so you can run over ice, right? Maybe you're in a sled pulling a sled. Okay? No, maybe you're in a snowmobile pulling a sled. Would that work? Yeah. That would be a good example. And you're on what used to be a lake, but now it's ice, right? And you speed up in your sledmobile. Okay, anyway, I'm trying to imagine something that'd be fun to do. Anyway, I forgot where I was going with that. What would have to be true with this rope? Could this rope ever go slack and that be true? Let's replace the rope with a rubber band. Would the rubber band have to stay stretched the same amount the whole time? Yes. Are you seeing it? So essentially the rope has to stay tight. It's not like when my dad towed me, my car broke down. This really happened. This thing is going to end up being 15 minutes. Who cares? My car broke down while I was going surfing with my friends, and he'd come down with a rope and tie. This is so illegal. I shouldn't say this. Don't ever do this. Okay? It's a bad idea. But he would tow me with this car, tie the rope to my bumper, and tow me home. All right? And I'd get screamed at because I'd try to keep the rope tight because I didn't like being jerked, right? And it's a bad noise when the bumper gets ripped off, right? So like, I would try to keep the rope tight, so I'd be stepping on the brakes sometimes. Like, in other words, I'm the person who's got to stop both cars, right? Because I'm in back being towed. My car's in neutral. This is very dangerous. Don't do this. I said that, right? I'm just kidding. I never did this. Anyway, if he's speeding up, the rope can stay tight, but once he starts slowing down, I have to use my brakes. Well, my timing wasn't always very good, and I just hear him yelling from the other car because I'd be stepping on the brakes at the wrong time, and he'd be trying to go, and I'd be stepping on the brakes, and he could feel it. Anyway, I thought it was funny. It wasn't funny. It was hard. Just getting yelled at from the car in front of you. I never had that happen before. From behind all the time. No, just kidding. I'll stop. This should be really easy now. What's this look like? The rope has to stay tight, linear with a slope, no slope. Is the force on the object changing?
No.
Thank you. I think the logic behind this is essential. Okay? So would you guys agree F delta X is equal to work? And we assume this all the time. We assume that the force on our system is constant, not changing. This is not a spring. When you pull on a spring and stretch it further, it requires more force the further you stretch it. Right? This is different. Okay, going back. So, I'll try to speed this up a little bit. Would you folks agree that I can plug in F delta X for work? Are you guys good there? You guys cool? Everybody good?
So is this true no matter what?
Yeah, we're deriving an equation for kinetic energy. But I created a simple situation two simple moments in time, but this will give us an equation for kinetic energy, energy stored in the motion of an object. That's what? EG is a different equation. Energy stored in a gravity field when you lift an object.
So we're just doing
I'm showing you how to figure out EK just theoretically. If you wanted EG, let's go back to this. When you lift an object, simplest case, you lift it with what kind of motion? Let's say I lift an object with constant velocity or constant acceleration. If that's true, is the force down and up equal? So the lift force due to your hand lifting this, has to be the same as the weight of this, if constant velocity. So if we assume that to be true, instead of delta x, can I call it h because I'm lifting upwards? And instead of F, you just agreed with me that the weight of the object is going to be equal to the force you lift with. So this is weight. So EG, now we're not talking about work, right? We're talking about energy stored in a gravity field. But it comes out of the definition of work, what we just did, is going to be weight, not work, I'm going to write it out, times the height I lift. Now, as you know, to calculate weight, you take your mass and you do what? And the 10 newtons per kilogram or 9.8 newtons per kilogram is a lowercase g. That's the symbol we use. So mg, and I like using a delta h to imply that it's a change in height that we really care about. You guys get it? So you're not limited to thinking that it has to be measured from the ground or something silly like that, which is not true. Cool? Are you guys good? Anyway, so going back. Okay, let me take this. Okay, is that the tension? This is the tension. If I do a force diagram for my object, weight, normal, tension. Would you folks agree? Weight, normal, tension. Everybody cool? If I sum the forces, I got force up, tension to the right, weight down. This is weight, normal, tension. Do you see that the net force, the sum of the forces, goes from here to here? Do you see that sum of the forces is that vector? Everybody good?
Yeah.
Do you see that this vector is the same length as my tension? In other words, the tension is my net force. And what's this equal to? There's a vector that's MA, same vector, right? You guys good? So can I go back, since tension is the force we're talking about, can I replace it with MA?
Yes.
You guys cool? Okay. So I'm going to take this and replace it with what, folks? We're actually almost done. And then this is delta x equals EK. Everybody cool?
F is sum of all forces?
Well, in this case, isn't F due to the rope? I could call this T if I want, right? Tension to the rope. But I just drew a force diagram. I summed the forces, and we figured out that the tension is the sum of the forces on this object.
Oh, yeah.
And the tension is the sum of the forces, and the sum of forces is MA, so I plugged in MA.
Gotcha.
You guys good?
Yeah.
Okay. Let's attack this. Let's get that out of the way. A, right? If you wanted a definition of A, and you drew a velocity time graph, if you wanted to draw a velocity and time graph, velocity versus time graph for, I'll wait till you guys are ready. If you wanted a velocity and time graph for a situation where something is speeding up, is accelerating to the right, as it is in this case, is everybody good there? The object's accelerating that way? Everybody's good? What's the velocity time graph going to look like? Straight line or curve?
Straight.
This should be easy, right? This is everything you've learned, right? And which part of this graph is your acceleration? Okay? And I'm going to remind you that this object, this example we created, started from rest and sped up, right? So this slope is equal to A. Acceleration is a vector, it has direction, and it's equal to change in velocity over change in time. Are you guys good? Which is the slope of this velocity time graph. Now, since we start at 0, when we do V final minus V initial is 0, right?
Yeah.
T final minus T initial is 0. So can I call, can I just label this, can I just say it's V over T? Are you guys good with that? So I can plug in V over T where I have A here. Is everybody cool?
Can you leave that up for a second?
Sure. So I can plug in V over T. These notes are going to be posted for you.
I know, but I like writing them
Okay, you may. Okay, now I want to attack this. Using that same velocity time graph we just had, which part of that graph is your displacement? How far the block moves? Good. Good. All right. So, here. I find this area. What is this area equal to? 1/2 what? 1/2 what? Can we call that V? Can we call this T? Are you guys okay? It's nice when you start at 0. It's like so much simpler. Yeah? That's why I had my object starting from rest. So now what am I going to do? What am I going to plug in where? People. And I think you should see the equation for kinetic energy right now. Do you? What am I plugging in here? Do you see it yet? If you don't see it, you should very quickly see it. What cancels? Isn't this beautiful? I mean, look. This is gone. This is gone. Rearranging it, making it pretty. EK is going to be 1/2 M. This is usually how you see it written. V squared. Done deal. Happy? Isn't that cute? All right, now let's talk about your lab results. Okay? Because this is where it's really going to help you. All right? Let me graph. You're supposed to have this graph, right, from your data, and it looks like that. What is this going to look like? If EK is proportional, if kinetic energy is proportional to the square velocity, what's this got to look like? Good. It's called a top opening parabola. So to linearize this, in other words, if kinetic energy is directly proportional to V squared, you got to square V, and you'll get a line, right? Now, here's the trick. This is where you'll know right away if it came out beautiful. You with me? When you write an equation in this line, y equals mx plus b, can I ignore b? If the velocity is 0, what should the kinetic energy be?
0.
So can I ignore my intercept? Should it be very close to 0?
Yes.
Okay? When I look at this, y is EK. Is that right? Y is EK. Are you guys good? This is the slope of this graph. And x is V squared. Am I right? We got V squared here, so that's x. So what's m gotta be? In terms of your mass, what's m gotta be? This m isn't mass, this is slope. Do you see how the slope has to be 1/2 m? This is the slope. This is the slope of this graph. Do you see why? You guys good? Yeah. You want me to show you a real group's data? Go.
So slope
Mass of what? Sometimes it helps to get concrete. Check it out. Let me go over here. This is, I'll post it, don't worry. This is better, it's real data. Okay? So check it out. Can you look at this and tell me if they nailed it? I'll give you a hint though. They did not have, I gotta tell you one thing. They didn't have just the car. Just the car alone is a mass of 1/4 of a kilogram. But they had this sensor. They accidentally left this Bluetooth sensor in the car, which makes it a total mass of 0.4 kilograms.
Oh, they got it right.
How do you know?
The slope is about half of this.
Look here. And look at the other cool thing. Okay, if you're wondering what a joule of energy is, imagine this. Okay? We've said many times that touching your phone, right? That's about a Newton. You guys with me? Well, if you touch your phone with a Newton of force, actually that doesn't make sense. Your phone is sitting on ice, and you touch your phone very gently and push it for a distance of 1 meter. So you push with this very gentle force for a distance of 1 meter. That's a joule, right? 1 Newton times 1 meter. You guys good? So if you push with a force of 1 Newton over a distance of 1 meter, you have transferred 1 joule of energy with your finger, right? Nothing. It's very small, right? No, Newton's times meter is a joule. Remember Newton meter, she's a joule? Remember the joke? Okay. Newton didn't go out much, and his friends were trying to set him up with a date, and he's like, they got all upset with him because he'd never go out. And they're like, Newton meter, she's a joule. Okay? I'm just trying to give you a way to remember it, okay? So, look at that. 3/100ths of a joule. The force for 1 Newton force over a distance of 1 meter, that's a joule. Now that amount of energy that you transferred to your phone by pushing it 1 meter, gently, right? That amount of energy, cut it into 100 pieces, and 3 pieces out of that 100. 3/100ths of a joule. Is this very large? Is this essentially 0? Is that a good sign?
Yes.
When you're not moving, velocity of 0, should your kinetic energy be 0? So that's a beautiful sign. And so you can just talk about this part of the equation, the EK versus MX. EK is kinetic energy, and M is 0.2, right? These units are, I got one more thing to do, I think you'll like it, joules per meter per second. It's actually meters squared per second squared. Do you see I'm getting these units from the units here divided by the units there?
Yes.
There's an error here. It's meters squared second squared, right? That whole thing is squared. Actually, they have it in a parentheses. They're okay there. They did good. There's no error there. It's all blocked in, so they're fine. It's meters squared per second squared, though. And then this is v squared, right? And if I take these units down here are joules. Is a joule a Newton times a meter?
Yes.
So let's just take the units joules over meter squared per second squared, right? A joule is a Newton times a meter. Meters squared, second squared. Can I ditch one of the meters here?
Yeah.
So I'm left with newtons over, and I'm going to write m instead of m squared. Second squared. Is everybody good there? Do you know what a Newton is? If you ever forget, go back to Newton's second law. Sum of the forces equals ma. This is how a Newton was defined anyway. So you're going back to where it came from anyway. Force is measured in what? Mass is measured in what? Acceleration is measured in? Good. All right. So I'm going to plug in for Newton. I'm going to plug in for Newton. What do I plug in? kg? Help me. So this slope, when the units are actually simplified, this is kilograms. Should it be? Because KE equals I'm going to block this in, 0.2 kilograms times V squared, because this 0.2 kilograms is what in general? This total is a mass of what? The mass of their system was a mass of what?
24.
And they're getting a mass of roughly 0.2 kilograms here.
How do you get what's the relationship between the 1/2 mass and the
What is the slope of your kinetic energy velocity squared graph? What is this slope? Say it loud.
Oh, it is 1/2 mass.
Is this half the mass of their system?
Yeah.
0.4 was the mass of their system, and they're getting 0.2. Did they nail it?
Yeah.
So now you have a beautiful way of checking your work. You guys good? I'm done unless there's more questions. What should you do in the time left?
Like 3 hours.
If it didn't work out and you can't figure out why, you think I'm available. I'm available now. I'm available lunch tomorrow. Please visit. A lot of groups are pretty happy figuring it out right now. Tomorrow we move on. Make sure your notebook's beautiful. Make sure you watch the videos, including, this one is just a review, so only watch things that didn't make sense. But make sure you know how to figure out EK, EG, elastic, you know how to figure out work, and you'll have the whole package. You guys good? All these videos will be up along with these notes. You go ahead and get started.